In this video, we'll look at how we can compute marginals in a linear chain conditional random field. So in the previous video, we've seen how we could compute the probability of a full sequence of labels y given x. To do this, we just take the exponential of the sum of the unary and pairwise factors, and then we have to divide by this partition function. In the previous video, we've seen how we can actually compute this partition function efficiently, even though it involves a lot of nested sums over all the potential labels at each position. By computing an alpha table or a beta table, we could actually, through a dynamic program, get a very efficient procedure that is not exponential in the size of the sequence for computing the partition function. So to do this, like I said, we had to pre-compute a table of that we call alpha, or a table that we call beta, for where each essentially computes the summation of the exponentiated log factors that involves all of the labels to either the left of a given position or to the right of a given position. And so now let's assume again that we've done this computation of either the alpha, actually of both the alpha and beta table. What we'll see now is an expression for how to compute marginals, marginal probability over the sequence. So for instance, the probability of a single label at a specific position k. And what we'll see is that this expression also requires the alpha and beta values. And specifically, we'll assume that we're using the stable implementation of the alpha and beta table, where we actually have a table that contains the log alpha and the log beta values. And this is, again, very important to actually implement that variant of the computation of the alpha and beta tables to get something that's numerically more stable. So now here we're interested in computing, and we'll see two particular marginals: the marginal over a specific position, so the probability of a single label in the sequence at a given position k, or the pairwise, the probability of a pair of labels at a position k again. So let's first look at this one, the marginal probability over a single position. Well, again, we'll use the alpha and beta tables. So remember that the alpha table essentially gives us the value of the log of the sum of the exponentiated log factors for all the potential labels to the left of a given position, and the beta gives us a similar computation, but for the log of the sum, so the log beta table is going to give us the log of the sum of the exponentiated unary and pairwise potentials to the right of some given position. Now, if we want to compute p of yk, position k, given x, well, that would correspond to the sum over y1 and the sum over y2 up to the sum over yk minus 1, then the sum over yk plus 1 up to the sum over y capital K of p of y, where y here would be in bold, that would be the whole sequence, given the sequence of inputs. Okay, so that's just marginalization, an operation that we know from probability theory gives us now the probability over just yk at the specific position k. And we've seen that the log alpha value and the log beta value actually gives us these summations. So log alpha value performs the summation over the labels from position 1 to k minus 1, and the log beta value gives us the log summation of the value of the label at position k plus 1 up to yk. So actually, specifically, this sum here is going to correspond to the alpha k minus 1 value. So remember, this index tells us from y1 to yk minus 1 that gives that this value corresponds to the summation of y1 up to yk minus 1. And then similarly, this sum here would correspond to beta k plus 1. That is, the k plus 1 means that we've summed from y capital K to yk plus 1. So I won't go in detail as to how we obtain this expression. I'll leave that as an exercise. But we can show that the probability of yk given the whole sequence x is just the exponential of the unary factor at position k. So our preference for whether we like seeing this specific value of yk at position k, plus, well, the log alpha values and the log beta values for where we assume that the label at position k is taking the value yk here and here. So these are the sums that are conditioned on the kth label being equal to yk, and same thing here. And now to get a probability distribution, we need to make sure that this is normalized, so we can just normalize the numerator, it turns out, and so we're summing over all potential values, which I'm going to name y prime k, of the numerator. So the exponential of the unary factor for the position k, if we assume the label takes y prime k as a value, and then the summation of everything to the left, assuming y prime, assuming the kth label takes value y prime k, and then the summation to the so to the left, the summation to the left, summation to the right, assuming that the kth label takes value y prime k. So actually this you can think of as just doing the softmax nonlinearity on the vectors of this term here, the log factor plus the log alpha and log beta values. And you know, the key to understanding why this makes sense is that the log alpha and the log beta values give us these sums over the everything to the left and everything to the right, which is a sum we have to perform if we want to marginalize out these labels and get the probability for only a single position. And similarly, using the same reasoning, if we want the probability of the kth label and the k plus 1th label taking value yk and yk plus 1, then we'll have that expression be the exponential of the unary factor for position k, also the unary factor for position k plus 1, plus the pairwise factor that expresses a preference between the label position k and k plus 1. And then plus, well, the summation of everything that's to the left, so from position 1 to k minus 1, and then everything that's to the right, so from position k plus 2 till the end, till position capital K. And again, to have this be a valid probability, we need to divide by the summation over all the values that the kth label could take and the k plus 1th label could take of the exponential of essentially exactly the same term. So we see the exponential term here is exactly this term. I've just replaced yk by y prime k, which is and yk plus 1 by y prime k plus 1. So again, this is also similar to a softmax operation, but this would be a softmax, a special softmax over if you want the matrix of activations for all values of yk and yk plus 1 for these sums of unary, pairwise, and log alpha, log beta terms. All right, so this is how you compute marginals in conditional random field. And the reason I explain this now is that in particular we'll want to use this to make a prediction. That's one procedure for performing classification of each at each position is going to be to use this. And we also use both of these marginals in the linear chain conditional random field when we'll want to train the conditional random field, which is going to be the topic of the videos for the following week.